For decades, physics and mathematics have operated in separate, isolated domains. They speak entirely different languages, locked inside their own rigid frameworks. Topology studies theoretical shapes. Information theory maps data and probability. Classical geometry maps gravity and space. Because these fields rarely interact, we lack a single architecture to explain how the universe actually operates from the bottom up. A theoretical framework emerging from independent research in Kazan, Russia, attempts to cross these boundaries. It is called the observer-dependent theory of everything, or ODTOE. The premise reverses the standard model of physics. Instead of a universe that exists passively while we watch it, the framework models the observer as the active constructor of physical geometry. To validate this, the paper performs a highly specific translation. It maps the subjective, cognitive act of observing a system into a strict, workable mathematical equation. Identifying that precise mathematical link is the necessary threshold to prove observation dictates physical structure. The framework starts with a concept called cognitive coherence, represented by the variable b. This measures how neatly an observer's internal state aligns with an external configuration. In standard statistics, researchers use a tool called the Kullback-Leibler, or KL, divergence. It calculates the exact mathematical difference between two probability distributions. The authors discovered a direct equivalence. The negative logarithm of cognitive coherence equals the KL divergence. The proof relies on specific modal weights of observation. An observer's internal weighting functions identically to the prior importance assigned to a statistical distribution. The internal psychology of taking in information operates on the exact same mathematical rules as external statistical probability. We can extend this logic into topology to find the physical shape formed when an observer engages in self-observation. The ODTOE framework treats the self-observation operator as a mathematical contraction, a process that continuously narrows down a space. On a closed Hilbert space, Banach's fixed-point theorem dictates that this narrowing cognitive loop eventually stabilizes into a single invariant coordinate. That stable point exists on a perfectly closed, simply connected three-dimensional sphere, denoted as S3. This S3 sphere connects the cognitive model directly to the work of Grigori Perelman. Perelman used this exact geometry and the Ricci flow to prove the Poincare conjecture, demonstrating how three-dimensional manifolds smooth and stabilize. The cognitive loop of a self-aware observer naturally assumes the exact topological shape required to stabilize the geometry of the surrounding universe. Tracing this topology to 2D geometry reveals the Archimedean defect. Subtracting an inscribed hexagon's perimeter from a unit circle circumference yields an exact defect of 2 times pi minus 3. Subtracting an inscribed dodecagon's area from the circle's area leaves exactly pi minus 3. These are entirely independent geometric measurements, but when you multiply the residuals from the length and the area together, you arrive at the square of pi minus 3. This pi minus 3 squared invariant functions as a foundational geometrical footprint, the exact residue left behind whenever a cognitive observer maps themselves onto reality. With the information and geometry established, the next step is bridging them together. In information theory, the Fisher metric is used to map the internal statistical geometry of an observer's mind. The paper reveals a complete structural match. The Fisher metric charting the mind aligns perfectly with the observer-correlator metric charting the physical space of gravity. The two grids lock into a single structure, precisely when the potential function equals the log probability of the observer's state. The subjective cognitive reality and the objective gravitational reality are written in the exact same mathematical syntax. The framework establishes the structural bridge, leaving one final open frontier, the synchronization of time itself. We have two separate clocks to reconcile. On one side is the geometric time of Perelman's Ricci flow, physically smoothing the universe. On the other is the internal time dictated by how fast the observer processes cognitive updates. The paper proposes an open timeline correspondence, hypothesizing that the physical flow of time is a direct mathematical function of the observer's cognitive coherence updates. The observer operates as a dynamic, looping phase that continuously projects itself onto the static geometry of space. The ODTOE framework presents reality as a continuous architectural construction, built and stabilized by the mathematical requirements of observation.